acetic acids are a pain. They don't completely dissociate, so you have to calculate them, okay? But it's everything you learned about acids works for bases as well. So calculate the pH of a 15 molar, ammonia solution. I just happen to have that right here for regular chemistry. There's a 15 molar ammonia solution. Isn't that exciting looking?
Yeah.
Drop it on some paper towels.
Well, ammonia won't, bases don't burn.
Oh, that's right.
KB, 1.8 times 10 to the minus 5. I've given you a reversible reaction for ammonia ionizing in water and becoming the ammonium ion plus hydroxide ions. It's important that you recognize those terms, ammonium, hydroxide, okay? So initially, for the NH3, 15M. For the NH4 plus and the OH minus, 0, 0.
We just like cross out these.
Don't put X because that means something else. Change for the NH3, minus X, plus X plus X. At equilibrium for the NH3, 15 minus X, but we're going to ignore the minus X because the KB is small. So just 15. Well, that's actually good. That saves you so much work. And for the NH4 plus X and for the OH minus X. Okay, good. I don't have to put this on the board so far. So KB, there's your equilibrium expression. NH4 plus the ammonium concentration times the hydroxide concentration divided by the ammonia. So it's going to be X squared over 15 equals 1.8 times 10 to the minus 5. Well, I got to slow down just to write that. I'm sorry. It's easier when I write it because I don't go too fast. Huh? So what we have so far is we've got X over 15. Okay, so it's X squared over 15 equals 1.8 times 10 to the minus 5. So we solve for X, and it's the hydroxide ion concentration. Okay, and it's 1.6 times 10 to the minus 2 moles per liter. What does that tell us? Well, here's where you go back to the top, method 1 or 2, whichever works for you. You now know the hydroxide ion concentration. So, whichever way you want to do it, Kw is 1 times 10 to the minus 14. That's equal to the H plus concentration times the hydroxide ion concentration. Solve for H plus. And then you get the pH. Negative log of whatever that is. So, that's one way you could do it. If you do that, you get H plus concentration is it's at the bottom there. See where it says concentration of H plus is equal to Kw over Kb.
So 1 times 10 to the
Okay.
negative 14.
Divided by 1.6 times 10 to the minus 2. That shouldn't be Kb actually. That should be just concentration of OH negative. My boo-boo on that one, I apologize. So at the bottom down here, right above poly product, it should say concentration of H plus is equal to Kw over concentration of OH minus. Should say this. My boo-boo on that one. I got a little overzealous. And so it's going to be 1 times 10 to the minus 14 divided by 1.6 times 10 to the minus 2 moles per liter. And it's 6.3 times 10 to the minus 13 moles per liter. If you take the negative log of that, you get 12.20 for a pH, which makes sense because it's a base. And if you rather have done the other method, it's right above that. It says POH is equal to the negative log of the OH. So since we already know the OH is 1.6 times 10 to the minus 2, you take the negative log of that, you get 1.80. So Subtract that from 14, you get 12.20, which is good, because that's the same answer. Whichever you prefer. Okay, I kind of went through that kind of quickly, so let you digest that. So the only difference between weak bases and strong bases is weak bases are more work. You have to do something to get to the point to where you can plug in one of those two methods. Okay? What is that, I'm sorry? I failed on that King B under right above poly product. I think that's the only boo-boo I made. Oh, I did a squiggle instead of a bracket. Oh, sue me. Call my lawyer. All right. Of course, I don't have one yet, so give me time.
I'll give you.
That's plenty of time.
Over here.
Yeah.
I got somebody in mind. Now.
Mr. Song.
Yeah.